Thank you for the introduction as well as the invitation to speak today. So the work that I'm talking about today is joint with Matt Satriano, and also, so for today I'm going to be working sort of with varieties over the ground field, the complex numbers. All right, so the beginning of this setup is that if we start off with X is going to be just some variety, and I need to put some technical condition on the type of singularities that show up, but it's not really important for this talk, but it's going to have log terminal singularities. And the idea is if you have some variety with log terminal singularities, then Batyrev gives you, he gave a recipe that spits out something that he called the Stringy Hodge numbers of X. And this talk, I'm going to denote them by HPQ with the subscript ST for stringy. And I'm not going to define these, but how should one think about them? Well, for one thing, I should think about them as a particular way of generalizing sort of the usual Hodge numbers of a smooth projective variety. So if your variety X is smooth, then the stringy Hodge numbers are just the usual Hodge numbers.
If it's smooth or compact, or if it's smooth only? Is it also for open varieties?
Yeah. So for smooth and compact, it's the usual Hodge numbers. For smooth not compact, it's the coefficients of the Hodge-Deligne polynomial.
Thanks.
Yeah, I might sweep that nuance under the table throughout the talk. When I say Hodge numbers, if something is not compact, you can think sort of these sort of virtual Hodge numbers. So they're sort of Hodge numbers, but for non-compact things, and they satisfy cut and paste. But beyond this, what's one way to think about these as I generalize to things that are singular? Well, one important case is that if y into x is a Crepin resolution of X, then the pq stringy Hodge number of X is going to be exactly equal to just the pq Hodge number of Y. So I think a good way to think about stringy Hodge numbers is that they're telling you, if you had a Crepin resolution, they're telling you what the Hodge numbers of that Crepin resolution is. And I believe before Batyrev introduced these, it wasn't actually known that if I had two Crepin resolutions of X, that they should have the same Hodge numbers. But that comes out as a direct consequence of showing that they're both equal to the stringy Hodge numbers of X.
Could you remind us what the Crepin resolution is?
Yeah, so it's a resolution of singularities where the relative canonical divisor is trivial. So you can think of this relative canonical divisor as being some measure of how much is this resolution really changing things, and a Crepin resolution is saying that there's sort of no discrepancy. So I think it was actually a joke on the idea that discrepancy, that no discrepancy should be Crepin. So for example, if I have a Crepin resolution, but then I start blowing things up, then I'm going to start adding a discrepancy. So you should sort of think that this is like, for example, if the exceptional locus is codimension at least 2, then you'll automatically have a Crepin resolution. So think of this as sort of being like a resolution that doesn't change too much about the singular variety X.
Thanks.
So there's a conjecture from Batyrev that goes back to 98 in the paper where he introduced stringy Hodge numbers. And he conjectured that if X is projective, but still it's allowed to be singular, then all of the stringy Hodge numbers should be non-negative. And so I think this conjecture sort of comes out of mirror symmetry, but it's also sort of by the way that these stringy Hodge numbers are defined, it's really a question about resolution of singularities and birational geometry. So there's some deep open question that is telling you about information about the way in which these varieties can be resolved, and it remains open to this day. And I should say, why is this a difficult conjecture? Why is it not obvious? So I should say that in general, your log terminal variety does not actually always admit a Krepin resolution. So you can't just sort of use the fact that these are the Hodge numbers of something, because they may not be the Hodge numbers of something. And in general, when you don't have a Krepin resolution, these stringy Hodge numbers, they have no interpretation as the dimension of a cohomology group. So and in fact, that's what you would really want to prove something like this, is you'd like to say, well, how do I get something non-negative? Well, it's the dimension of something. So you would like to find some sort of cohomological interpretation for these stringy Hodge numbers, which from the way they're sort of defined in terms of having a resolution of singularities, and then and how the relative canonical divisor of that resolution of singularities looks. So in general, you might not expect these things to sort of come from a cohomology group, but the conjecture is that hopefully they actually do, and that means that these things are non-negative. And by the way, one way that I like to think about stringy Hodge numbers is that they're sort of what the Hodge numbers of a Krepin resolution of X should be, regardless of whether or not X actually has a Krepin resolution. So there's a special case that I want to talk about today that's sort of the motivation for what Matt and I worked on, and are continuing to work on. But there's a special case where this answer is known, and I think it's really beautiful, the answer. So the special case is where the variety X has only quotient singularities. So locally, X is going to look like some smooth variety quotiented by some action of a finite group. Okay, so what is known in this case? Well, just sort of by definition, if something has only quotient singularities, then it's the so-called coarse moduli space of a smooth Deligne-Mumford stack. And I'm going to give a name for this smooth Deligne-Mumford stack, whose coarse moduli space is X. I'm going to call it, fancy X. It's going to be sort of the minimal one that does this. So there's a canonical one that you can give to anything with quotient singularities. And maybe a question one could ask is, well, should we think of the smooth Deligne-Mumford stack as some version of a Krepin resolution of X? In other words, if I allow stacky things to show up when I'm resolving singularities, is it fair to think of this sort of Deligne-Mumford stack here as some stacky version of a Krepin resolution of our singular variety X that we started with? And I think the answer to this is yes. There are many ways in which we should think of this as actually being some version of a Krepin resolution of X. And one way to and here's a theorem that gives an example of why we should think this. So this is a theorem due to Yasuda from 2003. And Yasuda proves that essentially that the stringy Hodge numbers of X are read off by this Deligne-Mumford stack. In the same way in this example, or in the property I said above about how the stringy Hodge numbers of X should be the Hodge numbers of a Krepin resolution, you have something like that here. So you have the stringy Hodge numbers of X. They turn out to be Hodge numbers of this smooth stack fancy X, but it's not quite right to just take the usual Hodge numbers. You need to take the so-called orbifold Hodge numbers of this Deligne-Mumford stack. And the nice thing about this right-hand side, these orbifold Hodge numbers, they actually are defined by a cohomology theory. So these are defined by the so-called orbifold cohomology of the stack. So in particular, we get that these Stringy Hodge numbers are the dimension of some type of cohomology group. So as a consequence, you get that Batyrev's conjecture holds in this setting. So I sort of think of this as, you know, the gold standard for an answer to this question, where you have, you know, you have your singular variety, and you want to give some cohomological interpretation or you know, you want to show that the Stringy Hodge numbers are non-negative. But even better than that, you give this really beautiful sort of interpretation in terms of some cohomology theory. Let's see, and I see that there's something in the chat. So let me take a look there. Are we assuming isomorphism in codimension 1? Yes. So the this Deligne-Mumford stack here, that's the sort of the canonical one over X, has this property where it's an isomorphism outside of codimension at least 2. Does that answer your question, Dan?
Thanks.
All right. So okay. So that's the case of quotient singularities. I like to think about it as, you know, you sort of can't get a better answer than that. And now I sort of want to say, okay, well, what can we say about you know, are there singularities that are worse than quotient singularities that we can talk about and maybe get something like this type of answer? And the approach that we take, so, you know, what is the setting we're looking at? So what is one way to get, in fact, much worse singularities than quotient singularities? So we could do the following. Instead of letting X being a quotient of something smooth by a finite group, we could let it be the quotient by you know, some positive dimensional algebraic group. So maybe X is the GIT quotient of a smooth variety. So I sort of say, okay, well, I kind of want to still think of this as some version of quotient singularities, but now, you know, it's not by a finite group, it's by some positive dimensional algebraic group, and the singularities get way nastier than this. You know, in particular, you know, if you take any toric variety, it's always going to be, it's always going to come up as sort of the quotient by a torus of some smooth variety, whereas in, you know, only the ones given by simplicial fans are going to have quotient singularities. And you might ask, okay, well, are the ingredients of this above story, are there nice replacements for those ingredients in this setting of allowing quotients by more you know, higher dimensional groups? So there are already some nice replacements for some of the ingredients above. So for example, you know, for quotient singularities, you're getting the coarse space of some smooth Deligne-Mumford stack. And in this case, you're not going to get, you know, the coarse space of a smooth Deligne-Mumford stack will be, by definition, have quotient singularities. So you're not going to be able to use Deligne-Mumford stacks. But what you can do is you can replace them with smooth Artin stacks. So now, and really, you know, one way to think about smooth Artin stacks is that instead of sort of looking like things quotiented by finite groups, it looks like, you know, things quotiented by algebraic groups. And another one of these ingredients as well, okay, what does the stack have to do with the singular variety we started off with? And for the quotient singularities case, well, we said, okay, this thing is the coarse moduli space of this smooth Deligne-Mumford stack. And it turns out we already have a replacement for coarse moduli spaces that works in higher generality, including for many, you know, it sort of works for the stack quotient of the semi-stable locus of some group action. So essentially, right. So if you're replacing Deligne-Mumford stacks with Artin stacks, the sort of more flexible notion instead of coarse moduli spaces is that of a good moduli space. So in other words, we could say, instead of saying, you know, we're working with something that's the coarse space of a Deligne-Mumford stack, we could talk about what are the varieties that are good moduli spaces of smooth Artin stacks. And that's some sort of, you know, looks like quotients by higher dimensional groups. But, you know, that's not the whole story above. So the motivating question for what we've been working on is what should play the role of orbifold cohomology. In other words, is there some natural cohomology theory on smooth Artin stacks that is reading off the stringy invariants of its good moduli space under some condition about it being something like a Kreppmann resolution. And at the moment this is completely open as to whether there's some cohomology theory like this playing this role. But today I want to talk about what I hope is a start in the direction of finding such a cohomology theory. So I think of the results I want to talk about today as being motivated by finding such an orbifold cohomology theory, and I'll sort of say why not only are they motivated by that, but hopefully why they will eventually point in the direction of what such a cohomology theory will be. Okay, but so to explain our approach to how we are trying to find this orbifold cohomology theory, I need to sort of restate some of the things I said above in a sort of more refined setting. I need to replace these Stringy Hodge numbers with some notions involving motivic integration. So let me just set up the groundwork for motivic integration. I'm not going to sort of say too much carefully about motivic integration, but let me just sort of set up some of the formal ideas so that I can explain what our approach is. So first of all, I want to start off with the Grothendieck ring of varieties. It turns out you don't just want that; you want to invert the class of the affine line, and then you want to take some completion with respect to some particular filtration induced by dimension of varieties. This the exact thing isn't so important, but the idea is, and in fact I'm gonna call this ring M sub k with a hat for this completion, and we should just think of this as some modified Grothendieck ring of varieties. And the point is that in motivic integration, or at least the version I'm going to talk about today, the integrals live in this ring. So as opposed to sort of usual integration theories, or integration on manifolds, integration on p-adic manifolds, where when I integrate some function, I get a number at the end. Here in motivic integration, you integrate some function and you get some element of this modified Grothendieck ring at the end. So somehow there's extra geometric content that this motivic integration is reading off. So the second ingredient that I want to introduce is the so-called arc scheme of the variety X we started with. So I'll use the notation L of X for this arc scheme. And what is this? Well, it's a space parametrizing the so-called arcs of X. So what are those? So these are maps from spec of k power series T to X. So these are sort of maps from formal germs of curves mapping to X, and these things are the so-called arcs of X. And you can show that I think Nash actually proved this, that or gave this construction. You can show that there's a way to give a scheme structure to this set of arcs. Now it's not sort of the type of thing that you are used to working with if you're okay, so it's in particular this thing is going to be infinite dimensional. So it's not, or as long as X is more than is not zero dimensional, this arc scheme is going to end up being this infinite dimensional thing. So keep in mind that it is sort of this, in some sense, strange object in that way. But regardless, it turns out there's a nice theory of integration on it called this motivic integration. So the next thing is that there's a motivic measure on this arc scheme. So I'm going to use the notation mu sub x. And what is this thing doing? Well, for certain subsets of arcs, so I'll call these the so-called measurable subsets. So I've given you some subset of arcs. I've said that it's it satisfies some condition to be worth calling measurable. And what does this motivic measure do? Well, it assigns some element of the Grothendieck ring, of this modified Grothendieck ring, to this measurable subset. So it has there's some volume of this measurable subset, but that volume isn't a number. It's an element of this modified Grothendieck ring. And the notation I want to use for what mu x assigns to this measurable set is I want to sort of use integral notation. So I'm going to say that now this is just notation, but it's supposed to be sort of leading notation, which is that I take this sort of measure and I integrate it over this measurable set. But I just mean that this thing is assigning some element of this modified Grothendieck ring here. to any of these measurable sets C. Okay, and a really important sort of formal property of this that is one reason that motivic integration, it was introduced by Kontsevich to study Hodge numbers of Calabi-Yau varieties. And why does it have anything to do with studying Hodge numbers? Well, a special case of this is that if the variety X that you start off with is smooth, then if I take the motivic measure of the whole set of arcs, then you get just the class of the variety X in this modified Groningen. And it turns out none of these so if you just have the class of X in the Groningen of varieties, that's enough to read off its Hodge numbers. It turns out the modifications we did don't mess that up. So this class does in fact see the usual Hodge numbers, or to be more precise, if X isn't compact, it sees the coefficients of the Hodge-Lane polynomial. All right, so this is sort of our maybe, we should think of this as a refinement of Hodge numbers, this motivic integration theory. And then it turns out along with this refinement of Hodge numbers, there's a nice way to similarly refine the notion of stringy Hodge numbers. So Denef and Lozère, they gave this refinement that I'm about to talk about. It's the so-called, it's what they call the Gorenstein measure. And I'm going to denote it as mu sub X, and then with a superscript of Gor for Gorenstein. And this is some measure, again, on the space of arcs of X. And the point is that this Gorenstein measure is to the motivic measure as stringy Hodge numbers are to the usual Hodge numbers. So what are some properties of this? Well, first of all, if I apply this measure to all of the arcs, then this thing actually does read off the stringy Hodge numbers of X. So in the sort of this last bullet point for usual motivic integration, this Gorenstein measure is sort of playing that role where this element is seeing the stringy Hodge numbers instead of the usual Hodge numbers. But the analogy actually goes further than that. So, it turns out if X is smooth, I said if X is smooth, the usual Hodge numbers are just or the stringy Hodge numbers are just the usual Hodge numbers. And in fact, if X is smooth, then this Gorenstein measure is just the usual, it's just the usual motivic measure. But better than that, we had this statement about how the stringy Hodge numbers are reading off the Hodge numbers of any Krepin resolution, and this Gorenstein measure is sort of doing the analogous thing. So if y to x is a Krepin resolution, then the Gorenstein measure of x is essentially just the usual motivic measure of its Krepin resolution y. So this is again, morally in the way that stringy Hodge numbers are the Hodge numbers of the Krepin resolution, regardless of whether or not you actually have a Krepin resolution. I like to think of the Gorenstein measure as being the motivic measure of a Krepin resolution, regardless of whether or not you actually have a Krepin resolution. Okay, and what is, why does this fit into this framework here about trying to get some cohomological interpretation of stringy Hodge numbers? Well, I want to actually state there's a stronger result that Yasuda actually proves than the one that I first stated. So his result about stringy Hodge numbers was really a consequence of the following theorem, which is that if X has only quotient singularities, and maybe calligraphic X is this canonical smoothly Mumford stack structure that you can put over it, then the Gorenstein measure of X, which I said is a refinement of the stringy Hodge numbers, it turns out that it's essentially just sort of an orbifold version of a motivic measure on this stack. So I put that in quotes because I don't quite want to define that, but let me sort of give a sense of what I mean by this. So what does Yasuda prove? Yasuda proves that if I want the Gorenstein measure of some measurable subset C, then I can rewrite that as a particular integral over the sort of some version of arcs of the stack. So I'll just say here this, I integrate over the preimage of C. So this is something in arcs of the stack. And then what goes inside this integral. So I don't just take the measure, the sort of motivic measure of this set. I do something slightly differently. I take some function that involves something called the ages of the inertia stack of X. And I integrate that with respect to some motivic measure over for the stack this motivic measure is sort of defined very similarly to how you define motivic measures for schemes, but sort of the thing that you do is you integrate this sort of special function that involves this thing involving the inertia stack. So I want to say a few things about that. So first of all, one should think of this as a change of variables formula. For the map from the Deligne-Mumford stack to its coarse moduli space X. So what do I mean by a change of variables formula? So these change of variables formula are sort of a main reason why motivic integration is useful. So, on one hand, motivic integration is reading off things like Hodge numbers and sort of cohomological invariants. But, what actually gives it its potency? It's the fact that if I sort of have, a resolution of singularities, or, I take birational modifications, I have some sort of change of variables formula that allows me to take my motivic integral on one thing and then replace it with motivic integral on some modification. And you can think of this as sort of like this is some motivic version of the change of variables formula, that maybe you teach in a calculus class. But it's sort of, and of course, change of variables formula, it's sort of based off the change of variables formula for manifolds and p-adic integration, but it's sort of this motivic version of it. So that already works for motivic integration for schemes. And what Yasuda proved is that you have something like this, where now the birational modification is no longer a scheme, but it's a stack. And you get this nice change of variables formula that tells you how to rewrite this Gorenstein measure in terms of some integral on the arcs of the stack. The second thing that I want to highlight is okay, so what are these ages of the inertia stack? Well, it turns out that these ages are exactly sort of part of the definition of orbifold cohomology. So if you care about the orbifold, or if you want to define the orbifold cohomology for a Deligne-Mumford stack, it turns out, so you look at the cohomology of pieces of its inertia stack, and then you have to shift it by these things called the ages. So if you just care about it in terms, as a graded group, so you just care about sort of dimensions of things, the point that I want to make is that this formula is actually telling you how you should define orbifold cohomology. So, the historical order of events was that orbifold cohomology had already been defined by Chen and Ruan, and then Yasuda proved that, this connection to stringy Hodge numbers. But the point is, the point I'm trying to make is that if you just look at the change of variables formula that Yasuda proved, which sort of a priori didn't need to have knowledge of orbifold cohomology. It's somehow that this change of variables formula, just from the motivic integration perspective, is telling you how you should define orbifold cohomology. So if you didn't know how to define orbifold cohomology, this result would tell you how to do it, at least as a graded group. So maybe the motivation for what I want to talk about today, so sort of the results that Matt and I have, are, is there some change of variables formula like this that works now in the setting of smooth Artin stacks instead of Deligne-Mumford stacks? And then the hope is that maybe in the future, this change of variables formula will tell you how one should find this cohomology theory, in the same way that Yasuda's change of variables formula has sort of all the information in it to tell you how to define orbifold cohomology for a Deligne-Mumford stack. Maybe I'll stop for a moment. Are there any questions at this point? Is it a good place to maybe pause and breather?
I had two related questions about what's on the board right now. So first, should we think of this map from curly x to x as somehow crepant, or is there some like relative canonical divisor that somehow goes inside this stuff involving the age? And the second question is, how should I think about the inertia stack? I don't know what that is.
Great. So let me answer both of those. So the first question, should we think, is there a reason to think of this Deligne-Mumford stack as giving a crepant resolution of X and not just any resolution of X? And the so there's many reasons why the answer is yes. So if you take this canonical one, so for example, I could take root stacks along the this stack. There's some construction called a root stack. It doesn't change the coarse moduli space, but it does change the stack. That will somehow make this thing no longer a crepant resolution. So there is sort of a canonical one that's sort of before you can take any root stacks. And it really does make sense to think of this as a crepant resolution for a couple reasons. So one, it's not just a crepant resolution, but the exceptional locus has codimension at least 2. So it's sort of, the relative canonical divisor sort of has to be trivial because there's sort of no exceptional, there's sort of no divisorial piece of the relative canonical divisor. So that's one way to think of it as crepant. But and in fact, there is a nice notion of canonical divisor on a smooth Deligne-Mumford stack. And if you use that, then the relative canonical divisor in this case will indeed be trivial. So this really is, you should definitely think of this as a crepant resolution, for sort of from maybe multiple reasons. Okay, the second question was yes. So how should I think about this inertia stack? So let me sort of say quickly, because the inertia stack doesn't really play too much of a role in what I want to talk about later. But let me just say, maybe a sense of this is that so if I have a stack, morally speaking, it's like a variety, but maybe I've sort of put some extra data at some of the points where I say, okay, this point has a group attached to it. Where maybe if this thing was coming as the quotient of some group, the idea is that that group should be sort of stabilizers of that group action. And this inertia stack is parametrizing sort of pairs, points, comma, an element of the stabilizer of that point. So this is this inertia stack is somehow information. It's somehow like taking the sort of the stacky information about the stabilizer groups and then sort of making it geometric in that you now have sort of something whose points even parameterize those groups instead of just having the stack structure with those groups. This inertia stack shows up all over the place. It showed up for Chen and Ron's orbifold cohomology sort of because of how it's, if you want to do, for example, Gromov-Witten theory on Deligne-Mumford stacks, this inertia stack plays a role because of sort of the evaluation maps sort of naturally live here instead of in the stack. But okay, so there's some really beautiful geometry of this. There's really beautiful geometry of why these ages are showing up and why this is what the form that Yasuda's theorem comes in. But at least what I'm going to talk about doesn't necessarily get into the technical details, or even there's a reason that I'll mention later why ours is sort of not going to involve the inertia stack, at least at this point in time. Does that sort of answer your questions?
Yes, thank you.
Great. All right, great. So okay, so now hopefully I've at least motivated why it would be interesting to have a change of variables formula like this in this more general setting of Artin stacks instead of Deligne-Mumford stacks. And this change of variables formula is exactly sort of the thing that Matt and I think we have sort of a sense of what it should be. So so now let me actually make my setting precise. So the variety X that so far has just been something where I can define stringy Hodge numbers. I want to restrict to the case where it's the good moduli space of a smooth Artin stack. So as I said before, for example, anything that's anything coming from GIT is going to be an example of this. So this is going to be the good moduli space of a smooth Artin stack. And furthermore, I want to assume something that sort of should play the role of this good moduli space, the stack being a crepant resolution. So I want the good moduli space map that goes from curly X to X. I want to assume it's it's a small resolution. So let me just say what I mean by that. So by that I mean it should be a birational map, and the exceptional locus should have codimension at least 2. So for schemes or for even for Dilley-Mumford stacks, this notion of small resolution implies being a crepant resolution because the relative canonicals, have to be sort of supported on the exceptional locus. At the moment, we don't actually, so it's actually a subtle issue of trying to define the canonical divisor on an Artin stack. So the motion, we don't have a precise meaning of what a crepant resolution should be. We sort of have some notions in the toric setting. I hope we're actually sort of approaching it based off of some more recent work we're doing that I think sort of I think we're close to hopefully close to having a sense of what crepant resolution should mean. But at least we have this more geometric notion, this sort of more directly geometric notion that should imply crepant resolution, and that totally makes sense here. So that's the condition that I want to consider here. And the main theorem that I want to state is that we have evidence that this really should be thought of as a small resolution or should be thought of as a crepant resolution from the perspective of stringy Hodge numbers. So the theorem due to Matt and myself is the following, which is that if this stack X is something called a fantastack, and by the way, this is where sort of the tropical toric geometry stuff is going to come up later in the talk. So what is a fantastack? Well, it's a kind of sort of a toric Artin stack. So if you'd like, you can think of this as being a theorem about the toric case of what we want. So if X is a fantastack, then we prove that you indeed get a change of variables formula. And it looks like the following. So, okay, so first of all, I want to look at the Gorenstein measure of some measurable subset of the arcs of X, and it's going to be related to, well, I take the pre-image of these arcs, and I get some arcs in the stack, and I take their motivic measure. And this motivic measure is just sort of defined in a very natural way. Just take pretty much the definition that you would use for schemes and replace scheme everywhere with Artin stack. There's nothing really, there's nothing difficult about defining this motivic measure. But the sort of interesting thing is that this is actually related to the Gorenstein measure in the following way. So I left this space here for a reason, which is you can't just take the Gorenstein measure, but you actually have to modify by this function that we call sep sub pi. And what is this function doing? That should be a curly brace. This function is taking an arc of X, and what is it spitting out? So it's spitting out the following number, which is that I take, so this number could be infinity, but it turns out in this case it's finite, sort of outside of a set of measure 0. It takes this arc and it says, okay, look at all of the arcs of the stack living above that arc and count how many there are. And that's going to be some number, and that's the function that we want to say. So so what is the moral here? The moral is that yes, we should think of this thing as being a crepant resolution, but there's something I swept under the rug earlier about Artin stacks, which is that, and it's the reason that we need to correct by this function that I call sep sub pi. Well, Artin stacks that aren't Dilley-Mumford stacks are always non-separated. So I sort of lied when I said about things being like a resolution of singularities. You sort of have to squint and allow for the fact that things can be non-separated. And this function sub pi, which is sort of measuring the failure of this of sort of arcs to lift uniquely, you should think of as some measure of the non-separatedness of the stack. So this measures, I like to think of this as measuring the degree to which this good moduli space map is non-separated. Okay. So the, hopefully this is starting to tell you that, okay, this Gorenstein measure is related to some stack integral, but there's this non-separatedness that needs to be corrected for in some fashion. And that's the theorem. And the hope is, that we're sort of playing with how you can make this work for things that aren't just the toric setting. But I do want to say at least a little bit about, at least some level of generality of what this theorem already is, which is that if you care about toric varieties, I'm in a tropical geometry seminar, so I hope most of you care about toric varieties. Everyone should care about toric varieties, not just tropical geometers. Anyway, so every toric variety X is always the good moduli space of a fantastack that satisfies the condition that this map from the fantastack to X is a small resolution. So in other words, this theorem is sort of already applying to, all toric varieties. So I at least am seeing information about stringy invariants of toric varieties from that. Let's see. So I want to bring up something that's maybe a little bit more. Oops, let's see. This looks like there's a question in the chat. So if E is an elliptic curve, then BE is an Artin stack that is not. Okay, so the question is that, so I said that things that aren't dually membered stacks should be non-separated. And here we have an elliptic curve, and I'm looking at the classifying space of the elliptic curve. And it's so it's not dually membered because it's got this stabilizer that's this infinite group, this elliptic curve. And I actually don't know. So usually,
isn't the definition of separated for a stack that the diagonal should be proper, and so B of a proper thing should be, the diagonal of B G is G.
Right. So the definition that I'm using for separatedness is that the diagonal is finite. So
okay. In that case, I completely agree. Yeah. Thanks.
Yeah, and this, actually somehow ours. I should say that our setting, the stabilizers are actually all affine groups. So somehow we're making the one that you're mentioning is somehow.
Yep.
So yeah, but that's right. So I'm using the note separateness means diagonal is finite. Yep. Great. So I want to say a little bit about, okay, I said that at least for fantastacks, this sep sub pi is this is a finite number outside of measure 0, but there's the possibility that you have some big piece of the arc space where sep sub pi is equal to 0, and that would tell you that somehow the right-hand side, the stacks or the arcs on the stack are somehow not seeing that piece of the arcs of X because you're integrating the function 0 over that piece. So I should say, this is somehow related to. There's a whole story about how this is related to Yasuda's work in the inertia stack, and how something like the inertia stack and twisted arcs are sort of one approach to dealing with this issue I'm talking about where sep sub pi is 0. But for today, I actually want to talk about sort of an orthogonal approach, which is, well, are there nice settings where sep sub pi just isn't 0 on big pieces of the space of arcs? And so, the point here is that if you really want to get the Gorenstein measure of X and therefore the Stringy Hodge numbers from these motivic integrations on the stack, you really want to be able to divide by sep pi. So in other words, you want to know when can I know that sep pi is sort of sufficiently, outside of measure 0 actually non-zero. And there's this conjecture that, all the examples that we've sort of written down, including for fantastacks, but also for some other things involving like SL2 stabilizers, they all satisfy this conjecture so far. But I think in some sense, this is more a gut instinct than a conjecture. It's somehow mysterious to us at the moment. But I think it's sort of an interesting thing interesting geometric statement on its own, which is that if the stabilizers the stabilizers of the stack are all special groups, and special groups in the sense of Serre, so this says that the torsors are all Zariski locally trivial, then our conjecture is that under this condition on the stabilizers of the stack, that this function sep sub pi is not equal to 0 outside a set of measure 0. Outside a set of measure 0. And sort of the way to think about this conjecture is saying that, we believe that if the stack has these particular types of stabilizers, then I should be able to lift almost all of my arcs of the singular thing to arcs of the stack. I mean, it's kind of a weird conjecture, but there seems to be something, there's something there. I don't know if this is the precise statement, but there does seem to be something there. And I should just say that as a theorem, this is true when the stack is a fantastack. So again, in the toric case, this conjecture is true. But we've actually, there's some nice examples involving SL2 stabilizers that are also examples where this works. So let me just, I haven't, before this project, I hadn't ever really thought about special groups. So let me sort of give a few examples just so you have a sense of the types of groups that are showing up. So there's the additive group GA is a special group. GM, and therefore all algebraic tori are special groups. The general linear group is a special group. SL is a special group. The symplectic group is a special group. Extensions of special groups are always special groups. So these types of groups, when they show up as the stabilizers, for some reason it seems like there's this, you always are able to sort of lift your arcs. What did I want to say? So I want to make one comment about these special groups. So it's true that if you are a special group, then you automatically have to be connected, and therefore, right, the only finite special group is the trivial one. So that's why I said this is sort of an orthogonal approach to Yasuda's, which is somehow this setting where we want, to try to divide by sep pi, this setting is somehow, it applies to stacks that, it applies to this class of Artin stacks that its sort of intersection with the class of Dewey-Mumford stacks is just algebraic space. It's just trivial stabilizer. So it's somehow, it's a very different looking geometry than Dewey-Mumford stacks. And I think this is I think there's something there that should be explored. I don't think this condition for stabilizers of Artin stacks has been all that has been explored all that much. So I think it's just on its own an interesting place to look. So maybe just to sort of summarize some of these results, if curly X is a fantastack with special stabilizers, and we have some nice combinatorial condition that reads that off, then sort of piecing these theorems together, you get the following, which is that if I want to read off the Gorenstein measure of all of L of X, which remember, this is the thing that tells us about our Stringy Hodge numbers, then I need to integrate, then you have a function to integrate over the arcs of the stack. And it's exactly just, take 1 over this sep pi function and compose it with, L of pi. So this is just the map induced by pi on the arc spaces. And the point here is that this right-hand side, this depends only on the stack. And you might ask, and I'm hoping that there's, that we are able to find some answer for this, is that, is there a cohomological interpretation of this? That's maybe the an end goal for some of these things is getting some sort of cohomological interpretation for this stack side of the integral. And that, as we can sort of see from this equality, a cohomological interpretation of this would be giving you a cohomological interpretation of the Stringy Hodge numbers of X. So that's sort of, that's maybe the longer term goal, but at the moment we sort of already have, we sort of have this change of variables formula, which I think is sort of rich geometrically on its own. And the moral is maybe that, as long as you're willing to sort of correct for non-separatedness, That's, I think, the main moral of the story is that you sort of have to correct for non-separatedness in some way. And once you've done that, then sort of change of variables formulas are showing up, and then hopefully some cohomological interpretation potentially as a consequence. So what I did say, though, I mentioned that I think that this change of variables formula already has some rich geometry built into it. And so let me talk a little bit about that. So I want to sort of end this talk. I'm going to give an example, an example using the toric picture that I hope illustrates what the geometry of such a change of variables formula is. So I haven't told you how to define the motivic measure. At the moment, this is sort of just all these things are just sort of formal statements that I've written down, and I haven't said, what is the actual geometry here? So first of all, I should say, for just the case of schemes, what is the geometry of a change of variables formula? Well, so I have maybe I have some birational modification or a resolution of singularities. The key to proving a change of variables formula, it turns out, is to control the fibers of a particular map. So it's to control the fibers of this map, which I haven't told you what these are, but L sub n of y to L sub n of x. So what is this? This is something called the space of n jets. So in particular, if n is 1, or if n is 0, this is just the map from y to x. If n is 1, this is just the map on the tangent bundles. But in general, you have these spaces of n jets. And the point of the change of variables formula is really a statement about what do the fibers of these maps look like. So it's sort of this explicit geometric statement. And it turns out that for n sufficiently large, the fibers are all just affine spaces. A sub r for actually, and for some explicit dimension r. So the point is, you want to prove some change of variables formula. Well, you control these fibers of these jet space maps. You show that they eventually just become affine spaces, and you can control the dimension of those affine spaces. And it turns out that somehow the definition of motivic integration just sort of formally from that geometric statement spits out a change of variables formula. So, when you hear change of variables formula in motivic integration, my hope is that you'll think this is something about controlling the fibers. How can I lift jets from X to the modification? Okay, and now I want to give an example that sort of says what happens illustrates what's happening in the case of these fantastacks, these toric stacks. That sort of looks something like this picture for schemes. And now I get to sort of draw some nice toric pictures. So what's the example we're going to look at? I'm going to let X be cut out by xy equals wz in A4. So this is there's a cone over a smooth quadric. And what does this have to do with our setup? Well, it turns out that X is the good moduli space of a fantastack. And what is that fantastack? Well, it's the following. I take A4 and I quotient out by the one-dimensional algebraic torus. And what's the action of this algebraic torus on A4 that I'm quotienting by? Well, it's I act on A, B, C, D. Well, in the first two coordinates, I act just with weight 1, so by T, and then I act by the inverse of T on the other two. So you can work out that if I take this action of GM on A4 and I consider the stack quotient, that its good moduli space is really this variety here, this cone over the smooth quadric. So it has this this interesting singular point at the cone point. Okay, so let me draw the toric picture here. So I don't really care about the non-toric picture for the moment. Let's focus on the toric picture. So let me first give the toric picture for the variety X. Well, this is the toric variety given by the following cone. So it's this three-dimensional cone. It's a square, or it's a cone over the square. So I take a square and at height 1 in R3, and I take the cone over that. And this three-dimensional cone here, which I can see is not a simplicial cone, so I have sort of non-quotient singularities. this is exactly giving me my variety X. Okay, so what about this fantastic, this toric Artin stack, curly X? Well, what is sort of the toric picture of this? So it's the toric, the sort of combinatorial data is the following: is that I have a map that I'm calling beta. It goes from the positive orthant of R4. And what is this map? Well, let me give some names to these first lattice points here. So maybe these first lattice points along these rays are V1 through V4. This map exactly picks out those first lattice points. So it takes the ith standard basis vector and it maps it to VI. So this map beta is exactly the sort of combinatorial data of this toric stack. And because I can't draw the positive orthant in R4, I'm just going to draw sort of a blob here for that. Okay, so what is we're trying to understand the fibers of these jet space maps that I mentioned. So let me start with an arc of X. It turns out there's something called the truncation of that. And this is going to give you some n jet of X. It's just sort of, taking your arc is about power series and just sort of truncate after the nth coefficient. That's sort of how you get this n jet from an arc. And remember, the thing that we're trying to understand is the fiber of this map over this jet phi sub n. So I'm going to let capital F be the fiber of this map of jet spaces over our chosen jet phi sub n. Okay, so now I get to sort of draw some more things. So how do I sort of make that a combinatorial thing? So it turns out there's some lattice point that I think it's fair to call trop of phi. And I'm gonna set trop of phi to be some lattice point W, or I'm gonna call it W. It's some lattice point in this cone. It's sort of the combinatorial type of this arc. It's just the data of knowing sort of the vanishing order of this arc along the pieces of the toric boundary. So you get some nice lattice point here. And what am I going to draw from this lattice point? Well, I'm going to draw the inverse image of that lattice point under this map beta. So it's going to be some line segment living in the positive orthant of R4. It's going to meet the boundary at some lattice points here, and maybe it also has some extra lattice points in the interior. Oh no, I see. Okay, we have some extra lattice points in the interior. So here's what ends up happening. It turns out that the number of these lattice points on beta inverse of W is exactly given by the sep sub pi map. And it's the sep sub pi map evaluating this arc phi. And furthermore, for n sufficiently large, one can show that the number of connected components of this fiber that we're trying to understand F is exactly equal to this number of these dots. So that's this number of connected components is why this sep pi function is showing up. And that means, okay, so there's a connected component corresponding to each of these lattice points, and I just want to understand what those connected components are. It turns out for these ones along the boundary, they're just affine spaces. But actually the ones inside are actually not affine spaces. So I'll call them F sub I. They're actually not schemes. They really are honest Artin stacks with sort of non-trivial stabilizers. But it's not so bad, because it turns out, although they're not affine spaces, there's something really close. So they look like an affine space quotiented by an action of a power of GA. So some sort of stacky version of an affine space. And in fact, there's a notion of class of this in the Gorenstein ring of varieties, and it's actually still just L to the R. It's just this R plus S minus the S, and you get L to the R. So these components are somehow, okay, they're stacks, but they're close enough to affine space to sort of read off their class in this modified Gorenstein ring. And at the end of the day, you get the class of this fiber, although it's not just sort of the class of an affine space, it's very close. You just count over, you need to count over these points and then add up, that's just going to weight this L sub R. So now there's the non-separatedness part that really does need to be corrected for. That's the sep sub pi. But the stacky part somehow doesn't really need to be corrected for. Somehow just it's sort of close enough already to affine space that it works to get sort of exactly the formal stuff you need to make the change of variables formula work. So maybe the moral of this example is that, or the moral of maybe this whole thing is that you should think that Artin stacks really, for this example really should be thought of as a way, you should allow them to resolve singularities with an Artin stack. That's sort of a generalizing to smooth Artin stacks is not a useless thing to do. You actually do get information from it. The type of thing you care about from resolutions of singularities, in particular stringy invariants is one example of this. But you need to really somehow correct for this non-separatedness, which I think is somehow that there's something new that has to go there to understand that. And so, this change of variables formula is one way to correct for this non-separatedness. And then also maybe another moral is just I think the geometry underlying this motivic integration change of variables formula, I think is quite pretty, that it has a sort of explicit thing where it looks like the scheme case where you have these affine spaces, but you sort of have stacky versions of that. And then of course, for a tropical seminar that, for these ones, you have this sort of explicit combinatorial control of what's happening here. So, I'd be happy to talk sort of more about how this looks in the Fantastic picture, but the point is you get to draw these fun combinatorial pictures involving maps of lattice points and things like that. So I think that's what I wanted to say today. Thanks.